Good morning.
Good morning. Good morning, everyone. Monday. Let's wait for 1 or 2 more minutes. Anyone has any questions about chapter 5 or in general? All right. 1 more minute. March is almost over. One more month, and then we'll be done with the semester. And it's flying too fast. All right. So, good morning, everyone. Happy Monday. Nice sunny out in Greensboro. I don't know wherever you all are. If you're in Greensboro, the weather is really good today. It's sunny, not windy. Hopefully, the week will stay like this. So last time we started chapter 5, and I noticed that your homework for chapter 5 is due on 30th, which is tomorrow. We may not be able to finish this chapter tomorrow, so I extended your homework assignment until April 2nd. And April 2nd is a holiday also, so you will get time to work on it if you cannot do it before that. But 199% we will be able to finish this chapter on Wednesday. Worst case, if something is left, we'll see. But as of now, homework for chapter 5 is due on Friday, and the quiz is due on Saturday. So it is not due tomorrow and Wednesday. So let's quickly review what we did in the last class. And Miss Minion is not joining us this week. So if you have any questions, you're writing in the chat. I will not be able to read. So either you can ask me after the class, or if something that I'm teaching and not making sense, then you can stop me and we can go over that part. So last class we started talking about sampling distribution. What is sampling distribution? When we are talking about law of large numbers in chapter 4, how that law connects here. And when we are talking about increasing the sample size, when we increase the sample size, what happened to our population mean and what happened to our population standard deviation. So last time we discussed that when we increase the sample size, the sample mean gets closer and closer to the population mean, and sample standard deviation will be this. Or you can say the variance is this. When you take the square root, you get this part, which is standard deviation, and this is your variance, variance of x. And we also talk about sampling distribution of sample mean. So that means we take a sample, we get a sample mean, we take another sample, sample mean. So when we collected the sample means of different samples and then take the mean of those samples, then we call those sample means. So we can say the means of all those sample means, and then we calculate another mean, then this is an unbiased estimator of your population mean. So that means it estimates your population mean, but again, it is not suffering from bias, or we eliminate the chances of bias first by doing the random sampling, and second by doing the sampling distribution of the sample mean. So if we are talking about an unbiased, what is an unbiased estimator of population mean? Sampling distribution of the sample mean is an unbiased estimator, and we discuss about unbiasedness or how to remove bias in chapter 3, and we are just using the same concept, but now we are extending our knowledge that we know how to remove bias or how to avoid bias, how to eliminate bias, and what happened when I have sampling distribution of the sample mean. I do not know my population mean. This is unknown to me, and I need to estimate this. So when I need to tell this is my population mean, how do I estimate? I use sample mean. And then when I'm using sample mean, how do I collect a sample? So this is basically when you collect a sample, you know that you are doing randomization. So start from here and then going this way. So we are estimating population mean using the sample mean, but how to get the sample mean? And when we are talking about sampling distribution of the sample mean, that is unbiased estimator. So it estimates our population mean and it is not suffering from bias. So we can use whatever our sampling distribution of the sample mean is and say that this is equal to our population mean. And I also told you that this is called the point estimate because we are talking about just one point. And when we create some room for error on both the side of this sample mean, we are talking about point interval estimate. Then we are creating a range where we are adding the margin of error and we are subtracting the margin of error. So this side, your x bar minus margin of error and x bar plus margin of, and your sample mean is in the middle. So then we are talking about interval estimate, which is our chapter 6 and chapter 7. We also discussed that when we increase our sample size, our sample mean gets closer and closer to the population mean mu, and we say that it's an unbiased estimator. What happened to our standard deviation? The standard deviation get closer and closer, or you can say that standard deviation shrink, or you can say the spread gets smaller and smaller when you increase the sample size. And you can try that using any software. Just take any sample of size 10 or 20, and then you look at their histogram or look at their distribution density curve, and then increase the sample size and then see does the shape of the distribution look exactly the same when you increase the size with specific mean let's say you take a mean of 0.5 or point or 1 or 5, whatever makes sense to you or whatever you want to take, and then from out of 1 to 100, let's say you pick a sample of size 25 and then draw it, either a density curve or a histogram. And when you hit the command that histogram or density curve, then you will see that what is the shape of the distribution. You can check it either from the histogram or from a density curve or a density curve on top of a histogram. Let's say I have this, and then I can draw density curve, and I know that this is a right skewed distribution. Now, instead of 25, if I increase a sample of size to 50, is my distribution still looking like a skewed distribution, or is it getting better? And what happened to my spread? Is it getting far, or is it getting closer to the mean? So when you increase the sample size, and when you do it in a software or and I think on your Launchpad also there are some statistical applets where you can just plug the numbers and it will draw the histogram and the density curve. Then you can see that when you keep on increasing the sample size, your spread becomes closer and closer to the mean. And why? Because your sample is increasing and your spread is decreasing by how much? Depending upon what your sample size is. So sample mean get closer and closer to the population mean, and standard deviation gets smaller and smaller depending upon what your sample size is. So this is what we did in the last class. And I think we stop at central limit theorem. So let me talk about that part. So this is what we just discussed. The sample mean gets closer and closer, and sampling distribution of the sample mean is an unbiased estimator of the population mean, and spread gets smaller than the standard deviation of the population by square root of n. And why square root of n? Because we cannot find standard deviation, we can find variance. So variance is sigma squared, and when we are looking for variance in the sampling distribution, it's sigma squared over n. And then when you are looking for standard deviation, you are doing the square root of that. And when you do the square root of sigma square, it's sigma, and this is square root of n. So that's why it says that it reduced by the square root of n. So central limit theorem, again, this is the important application, or very, what did I say? Very important discovery kind of thing in a statistic, because central limit theorem help us to work with non-normal distribution also as approximately normal. So when we say our distribution is normal, it's easy. We know that the mean is mu and standard variance is this. But when the distribution is not normal, how do I work? So when the distribution is not normal, I cannot use my mean as mu and variance as sigma square, or standard deviation as this. If it's not normal, this is only for normal. And we also know that when we work with normal distribution, we can use 68, 99, 95, and 99.7% rule also to find the area, or to find the spread around the mean. And we say that 68% of the area is within one standard deviation, 95 is within two, and 99 is within three standard deviation. But what happens if the distribution is not normal? So central limit theorem, again, we are not proving the central limit theorem here. We are using the result of central limit theorem here. That central limit theorem tells us, like as the word says, center limit. So you apply the limit in the center. So it says that as the sample size increases, no matter what the shape of the distribution is, the shape can be left skewed, right skewed, no matter what the shape of the distribution is, as your sample size increases, your distribution becomes approximately normal with mean mu and standard deviation this. So when we are saying when we increase the sample size, no matter what the shape of the distribution is, we can still work this distribution as approximately normal, but now my mean is mu and standard deviation is this. And why this? Because we are increasing the sample size. So this is the normal distribution. But when we say we are using approximately normal, and we just discussed that as you increase the sample size, your sample mean get closer and closer to population mean, and standard deviation reduces by a factor of square root of n. So central limit theorem help us to work with non-normal distribution also. And again, when you have a normal distribution, it's easy to find, or it's easy to work with. But when it's skewed distribution, we know that we use median as the center. We don't use mean as the center when we work with skewed distribution. But if our sample size is large enough, we can use mean as the center, and we can say that sample mean is approximately equal to or your population mean, and the standard deviation is this. So let me read the exact or the proper definition of central limit theorem. Most population distribution are not normal. If we get normal, we are lucky and we can just work with mu and sigma. But what happens if our distribution is not normal? What is the shape of the sampling distribution of the sample means when the population distribution is not normal? And then it says that it's a remarkable fact as the sample size increases, the distribution of sample mean begins to look more and more like a normal distribution. Again, what should be the sample size to say that it is approximately normal? And am I saying the sample size should be large? The definition of large is different for different projects or different distribution or different samples. So when we are saying large, we are taking it n greater than equal to 30. So we are saying 30 or more. And again, when we are looking for a specific study, we will work on depending upon what kind of study we are doing it. So if the study is talking about the population of the United States, then this 30 is again too small. Then we will look at what is the population, what kind of sample size or how much sample size I can afford. And again, we will talk about how to look at the sample size, what should be the sample size if I know the standard deviation. So if I know a specific standard deviation, I can find my sample size. Let's say if I have a sample of size 20 and standard deviation of 2.4, but now I want to increase my standard deviation or decrease the standard deviation. And then I need to check, is my sample size 20 enough? If I increase my standard deviation from 2.4 to 3.6, or do I need to increase my sample size? Then again, you have a formula that you can use to calculate your standard deviation or your sample size, depending upon what standard deviation is given to you. And that formula is not given in your slides, but it is given in your Stat 108 notes. There is a homework question that is asking you to find the sample size. So let me quickly show it to you so you can write it down in your notes. So here is that. And these notes are again on your canvas under Stat 108 chapter notes. So here it says that suppose x bar is the mean of a simple random sample of size n drawn from a large population with mean mu and standard deviation sigma. Then the sampling distribution of x bar has mean mu and standard deviation sigma over square root of n that we just discussed. And it says that if you're looking for the sample size, what should be your sample size that you need to work with? Then look, this is your given standard deviation. So you can write as given standard deviation. And then it says what standard deviation you want to change. So I said that if my standard deviation is 2.4 and I want to say that, and my sample size is something, let's say 20 or 30, and I want to see if this sample size is large enough, if I increase my standard deviation to 3.2, or do I need to get a smaller sample size, then you can say this is the given standard deviation and this is the desired standard deviation that you want to change, and then do the square. So you can check it. Your given is 2.4 and you want to change it to 3.2 and then do the square. And then it will give you, when you divide it, you get some number. And obviously here, most probably you will get an answer in the decimal. Let's say I'm just writing a number, 21.27. I don't know if it's exactly the same. So if 21.7, then it says that this is greater than equal to n. N is greater than equal to this. If you're saying n is greater than equal to 21.27, and I'm talking about n as my sample, and my sample cannot be in fractions, so round off to the next whole number. So your n should be 22. So if I'm saying I solve for n and I get a decimal or fraction, I round it to the next whole number. Though mathematically, this will round to 21. But think of that as if we are taking a sample of size 21, we are doing under coverage because my n is 21.27. So I'll move to the next whole number. So I'm taking a sample of size 22 instead of 21 because it says that greater than or equal to. So when you are taking a sample, and let's say that sample is that subject is human or animal, we cannot take a part of that in our sample. We need a whole number. So if you're talking about the sample, or if you're looking for what is the right sample size I need to take when I change my standard deviation, then make sure you convert it into the next whole number, even though it's mathematically rounded to 21. But we are not talking about the mathematics here. We are talking about the sample, and the sample cannot be in the fraction, and we cannot go lower. We can go to the higher bound. So we will round it to the next whole number. So this is one thing I want you guys to know, which is not in the slide, but you will have that question in your homework assignment, and it's in your book. So what should be the n? N should be greater than equal to given standard deviation or provided standard deviation or the standard deviation that you are using. And this is desired standard deviation that you want to change, and then do the square. And this should be greater than equal to. So let's say we solve this one and we get this. So you can say my n is 22. So you are rounding it to the next whole number, even if it's mathematically correct or incorrect, statistically that is correct. Questions about this? how to find the right sample size. And so here we are talking about only when the standard deviation is given and both standard deviations are given. You cannot solve this if you know only one and you do not know the second one. So you can solve it only when you know both. Questions? So again, central limit theorem. We are going to use central limit theorem, and central limit theorem, you can say that what we did in chapter 1, how to find the z-score, we are using the same concept here, but now our standard deviation, instead of earlier we had z equals x minus mu over sigma, and this is for normal distribution, right? And now we are also finding z again here, but now we are talking about approximately normal. And approximately normal means that the distribution is not normal. It is skewed to the left or right, but my sample size is large enough. And when my sample size is large enough, I'm talking about approximately normal, but now my standard deviation is not sigma. It's sigma over square root of n. So my z will be x minus mu over sigma over square root of n. So in this chapter, you are going to do what you have done in previous chapter, but instead of sigma, now you are working on this. So you are looking for the value of n also, and then you are dividing, and you are doing exactly the same what you have done in chapter 1, chapter 4, just as I'm saying that this chapter or each chapter is built upon your previous knowledge. So you did this in chapter 1, we use this concept in chapter 4, and now again we are further expanding, and now we are saying that even though I know it's not a normal distribution, but I can work with that as an approximately normal. How? If my sample size is large enough, I can work at approximately normal by changing my standard deviation or divide my standard deviation with the square root of my sample size. And then this will be my mu z, and then whatever value I get from here, then let's say z is 0.81, then I'm looking for greater or less, whatever the question is saying, going to the table, find the value, and that's my answer. Or you can use your calculator, normal CDF, and then you can find it. And we will do an example so it will make more sense. Anyone has any questions for me? All right. So central limit theorem, the same concept that we just learned. Let's see how do we use it in the problems. And you have a lot of problems in your homework assignment where you are using the central limit approach. So based on service record from the past year, the time that a technician required to complete preventive maintenance on an air condition follows a distribution that is strongly right skewed. So it is given to us that the distribution is right skewed. And if you look at this, you can see that the distribution is right skewed. And whose mostly likely whose mostly likely outcomes are close to 0. The mean time is 1, and it is given that mu is 1 and 1 hour, and the standard deviation is sigma. So I know that mean is 1 and standard deviation is also 1. So this is given to us. Now the company is saying that there is a simple random sample of 70 air conditioners. So now we have the simple random sample of 70 air conditioners. We know that this distribution is not normal. So I cannot use this word normal here or this letter n because I know that the distribution is strongly skewed. But I know that mean is mu 1 and standard deviation is 1. So I cannot use this because I know that this distribution is right skewed, or in the question they mentioned that it's strongly right skewed. Now I don't know that the distribution is right skewed and mean and standard deviation is given. I know if the distribution is skewed, I don't use mean as the center. I use median as the center, and then I don't use standard deviation as the spread. We use quartile as the spread. Now I don't have information for median and I don't have information for quartile. So what am I going to do with this? So let's see what the question is giving us in the next sentence. It says that your company will service a simple random sample of 70 air conditioners. So your sample size is 70. Now the question is, saying you have budgeted 1.1 hour per unit. So your X is 1.1. Will this be enough? So you're checking, will this be enough? Enough means what percentage I have. Will that be enough? Do I need to increase my budget? So if I need to do that, I need to do my Z score, or I need to find my area under the curve. But since my distribution is right skewed, I cannot work that as normal distribution. But let me check if my central limit theorem applies here. And the central limit theorem says that if your sample size is larger or equal to 30, you can apply central limit theorem, and then you can say that distribution is approximately normal with mean mu and standard deviation this. And since 70 is larger than 30, then that means I can apply my central limit theorem here, and I can use this distribution as approximately normal. And in the question, it says that strongly skewed, strongly right skewed. But central limit theorem, a powerful result that help us to work this as approximately normal, though it is heavily right skewed. Why? Because I have a larger sample size. So even if you have distribution that is skewed in any direction, you can still work as approximately normal with mean mu and standard deviation this if your sample size is large enough. And that is the case here. So I can find my mu and sigma. So you know that your mu is 1, approximately normal. So mu is 1 from here. And standard deviation sigma is given as 1, and sample size is square root of 70. So this is your distribution now. This is your approximately normal distribution with mean 1 and standard deviation this. And now you can find your z, x minus mu over sigma. And your x is 1.1, that is they are asking if it's greater, mu is 1, and standard deviation that you calculated. And then you can get the z value, go to the table and look at that value, and you will get the answer. And again, if you do not want to go through Z and table A, you can always use your calculator that you have done before. Normal CDF, mean, standard deviation. Oh, sorry. First you do your lower, upper, mean, and standard deviation. So your standard deviation is this now. So change this, and then you get lower is you're looking for 1.1, and your upper is how much? 999. Mean is 1, and standard deviation, and you can solve it. So again, whatever we have done before, we are just using the same concept. This is the only extra part we are doing. You can, if you don't want to do that way, you can do this also, sigma over square root of n, and then do that part. Either you do it here and then just straight plug, or if you don't want to do it here, you can plug these values here. And let's see how they solve it. So they said that the mean and the standard deviation of the sampling distribution of the average time spending working on 70 units. So mean is given as 1, and standard deviation 1 over square root of 70, which we calculated. So now they are approximately normal with mean 1 and standard deviation this, or 1 over square root of 70, whichever you want to write. And the central limit theorem says that sampling distribution of the sample mean time spent working is approximately normal because our sample size is larger than 30. And this is exactly what we did. And then you, since we are saying greater than 0.83, you can look at the value and subtract from 1, or you can use calculator. Once you get the result, convert into percentages, and then you can explain or do the inferences depending upon what the question is asking. It was asking, will 1.1 be enough? So it says that your budget 1.1 hour per limit, there is a 20% chance that your sample size will be larger than 30. And then you can calculate the z value, and then you can apply the central limit theorem and get the answer. And that is the answer. So this is your And when the spread is shrinking, the shape is looking more like a normal distribution. So we are on the last part. And again, this is also very important. Binomial distribution. What is binomial distribution? How do we work with that? What is factorial? What is the formula for binomial? And as the word says binomial, we are talking about bi means two, where we are talking about a distribution that has only two outcomes. We are talking about binomial. So before doing binomial, there is another distribution where binomial distribution is coming from. It is not mentioned in your slide, but I just want to let you guys know so that when you know binomial distribution, you know where is it actually coming from. So there is another distribution called Bernoulli distribution. You guys can see my screen?
Yes.
Okay, thank you. Just want to make sure. So Bernoulli distribution. When we are saying Bernoulli distribution, and sometimes we also say that Bernoulli random variable. So when we are talking about Bernoulli distribution, Bernoulli trial, or Bernoulli random variable, it is a trial in which only two outcomes are possible. So only two outcomes. A trial in which only two outcomes are possible. And when we are saying only two outcomes are possible, one outcome we say success, and another outcome we say failure. Success and failure. Let's say I'm tossing a coin and I'm looking for a head. Then head is my success and tail is my failure. Or if I'm tossing a coin and I'm looking for the probability of tail, then tail is my success. So there are two outcomes, one I'm looking for, one I'm not looking for. So one is called your success, and another one is called your failure. But we are only talking about two possibilities. And we can also say that true, false. Only two possibility of a question, either a true or false. We are not using maybe. And the other one is 0, 1. Or if the answer to this question is yes or no. So where we are talking about only two outcomes, we are talking about Bernoulli trials. So when we are talking about Bernoulli trial, we are saying that let's say my x is the random variable. So when we are talking about yes or no, or true or false, we are talking about two outcomes. When we add the sum of both, it should be 1 because the probability can max be 1. So when we are saying that success, then the success, if we are saying 1 with the probability of success and 0 when with the probability of failure. And we know that p plus 1 minus p is 1. So probability of success plus probability of failure should add up to 1 whole. So if we add this, success plus failure, probability should add up to 1. And if you see that, if you cross out, you get 1. So when we are talking about Bernoulli trials, we are getting only two outcomes. One has the probability of success and another one has the probability of failure. So let me say that x is the number of successes, or you can say y, number of successes in one Bernoulli trial. Then, so number of success, either no success or one success. That's all we can have, right? When we toss a coin one time, so either I get a success or a failure. So one success or no success. So success probability is P and failure probability is 1 minus P. And once we have this table, we know how to calculate the expected value and how to calculate the standard deviation or variance. And how to do that? We know that the formula is xi times the probability of the success and the failure. So this time this and this time this. So this will be 0 times 1 minus p. So my expected value, or you can say the mean, is probability of success. So this is for Bernoulli trial. I have not talked about binomial yet, but once you understand Bernoulli, binomial is not the hard part. Any questions so far? How did we get that? So we are talking about a trial that has only two outcomes, and one is called my success, another one is called my failure. The sum of success and failure altogether add up to be 1. So if my probability of success is p, the probability of failure will be 1 minus p. When you add both, it should be 1. So if one is p, the other should be 1 minus p. So when we are talking about success and failure, we make a discrete table. So only two outcomes, either a success or a failure. So this is my success and this is my failure. And the success failure changes. Maybe head is my success, maybe tail is your success. So then your probability of success, P, is for tail, and for me, it is for head. And expected value, chapter 4, we talk about it, how to calculate the expected value. So to find the expected value, you multiply with the probability and you get this. Or you can say that mu of x. So mu of x is p for Bernoulli trial. And how do we find the variance or the standard deviation? So let's find the variance first. We know that the variance is summation of xi minus the mean times the corresponding probability. So let's do that. So this is 0. 0 minus the mean is p square times the corresponding probability 1 minus p plus then 1 minus p square times the corresponding probability. This is what we did in chapter 4, just using the same concept. And then when you solve it, you will get p square 1 minus p plus 1 minus p square times p, right? So you can take 1 minus p and 1 of the p common. So you get p minus 1 minus p, right? No, plus. So I took 1 minus p and 1 of the p common. And from here I have left only 1 p, and here I am left with 1 minus p. And p 1 minus p times p. And when you open the brackets, this will cancel out. And then you are left with p 1 minus p. And that is your variance of x. So once you calculate the variance, finding the standard deviation is not the hard part. Can you tell me what will be the standard deviation? Anyone? We have the variance. How do we find the standard deviation? Anyone?
Square root.
Square root, right. Just the square root of what you just found. So you can calculate your standard deviation from the variance by just doing the square root. So we calculate the mean. Mean is P, probability of success, and standard deviation. Variance is probability of success times the probability of failure, and standard deviation is the square root of their product. This is the probability of success. This is the probability of failure. So this is what, when we are talking about Bernoulli trial. So when we are talking about Bernoulli, we are saying a trial that has only two outcomes. If I'm using the same trial and I'm looking for, let's say I'm tossing a coin 10 times, and I'm looking for how many times I get head. So that means I'm talking about 10 Bernoulli trials. So 10 Bernoulli trials means I'm talking about tossing a coin 10 times. And each time I have only two outcomes possible, either a head or a tail. So I'm talking about 10 independent and identical Bernoulli trials. So independent, we learned that independent, that means when I toss a coin, get a head in the first trial, it's not going to change my chances of getting a head in another trial or tail in another trial. And identical means if I toss a coin one time, I'm not tossing a die for the second time or something else. So identical, if I'm tossing a coin, I will toss the coin for all 10 trials. So when I'm talking about independent and identical Bernoulli trials, we are talking about binomial distribution. So binomial distribution, if you look at the notes and in the slide in the book, they're not talking about Bernoulli distribution. But again, it's good idea, or it's good to know that where is this distribution coming from. So binomial distribution is talking about independent and identical and Bernoulli trials. And that is your binomial trial. So binomial trial consists of the following sequence of pre-specified independent and identical Bernoulli trials. And sometimes we say IID, and IID refers to independent and identical. So when we are talking about n can be 5, n can be 10, n can be 20, n can be any number. If I'm tossing a coin 10 times and my success is how many heads or how many times I get head, then my n is 10. And my success is head. In each trial, I'm looking for the probability of success for the as a head. And trail is my how many times I got the failure. So when we are talking about binomial distribution, we know what a Bernoulli distribution mean is. Mean for the Bernoulli distribution is P, and the standard deviation is P1 minus P. Or let me just write variance also. First, let's write variance because standard deviation comes from there. So variance of x is P1 minus P. Now, when you know that you are doing the same thing what you are doing in Bernoulli trial, in binomial you are talking about n trials, but everything else is same. So mean for binomial, and this is Bernoulli. So you're doing what you are doing in Bernoulli, but you're talking about n times. So mean for binomial is n times p. So probability of success depending upon how many times you get that success. I toss a coin 10 times and I'm looking for how many heads I get. Let's say I get 2 heads. So then it will be 2 times the probability of head. So n is number of trials or how many times I am looking for the success and what is the probability of that success. And variance, same thing, variance of x is n times the probability of success minus the probability of failure. And similarly, when you are doing the standard deviation, you do the square root of that. So that will give you the mean and variance for binomial distribution. And again, you do not need to memorize those. If you understand what a binomial distribution is, binomial distribution, we write it as that, let's say, x is binomial distribution. When we are saying x is binomial distribution, we have two parameters, like how in normal distribution we have mean and standard deviation. And again, we discuss what parameter is, what statistic is. So parameter comes from the population and statistic comes from the sample. When we are talking about binomial distribution also has two parameters. One is the number of trials, and the second one is the probability of success. So binomial distribution, some places you just see this or this. So in your book, in your homework, in your quiz, you will see all these notation. They talk about the same thing. The only thing that you need to know that first is your number of trials and second is your probability of success. And when you are talking about mean is the product of these two. If you see that, mean is NP and mean is the product of both of your parameters. And standard deviation, mean product of these times the probability of failure and do the square root. So this part is not hard to remember if you understand what actually what information we have. We have only a number of trials and the probability of success. So when we are talking about number of trials and probability of success, we talk about binomial distribution. And again, it has two parameters like normal distribution. Sometimes working with binomial distribution is very complicated because it needs a lot of calculation. So we approximate binomial distribution to normal distribution, and we call it as binomial approximation. And I don't have enough time today to talk about it. We will talk about that in the next class. But binomial distribution is good when our x is not too large. But when we are looking for something very large, we cannot work with binomial distribution. Then we need to do the approximation to normal distribution. And again, when we are doing approximation, we need to satisfy some conditions. So when we are talking about this, and when our x is very large, then we will check if np is greater than equal to 10 and n1 minus p is greater than equal to 10. If these two conditions satisfy, then we can say that yes, we can approximate it to binomial distribution. But we will talk about it. So when we are talking about binomial distribution, so we are saying that x is a random variable which is binomially distributed with two parameters, n as the number of trials and p is the probability of success. When we work with binomial distribution, we use this. And what is this? These are the conditions that we need to check before we work with binomial distribution, and we call it as bins. Again, you don't have to go through that, but this is easier to understand. B means binary. So the outcomes are binary, either success or failure, or you can say like two outcomes. That way it's easier. So the outcome should be only two. So if I'm rolling a die, that is not binary because I get six outcomes. So only two outcomes, then we are talking about binary. And then I specifies independent. The trials are independent of each other. One is not going to affect the probability or the chance of other. And number of trials are fixed ahead of time. So if you're talking about looking at two heads in how many trials, that n should be fixed ahead of time. That n number of trials are 10, 15, 20. So this should be fixed. And S means success probability. And what is that means? The probability of success is same in each trial. So if I'm tossing a coin 10 times, the probability of getting ahead is 50, then it is 50 in all the trials. Or let's say it's not a balanced coin, and the probability of getting ahead is 60, then it is 60 in all the trials and 40 for tail in all the trials. It's not like first time I toss a coin, the probability is 50-50. I'm not happy. Let me change it to 60 and 40 and then 30 and 70. So it's not going to work. The probability of success, what is in first trial, should be same in all of your trials. And same thing, probability of failure is same in all the trials. And this is what it's given to you here in this. So take a look at that. And this is the only part that is left, how to use binomial distribution and do the normal approximations if our x is very large. And we will talk about that in the next class. And we will do, if time permits, we will do some practice problems. If not, I will upload those practice problems on Canvas. You try to work on it, and then I'll upload the solutions as well. Thank you, everyone. If you guys have any questions, let's have a wonderful afternoon.
Thank you.
You're welcome.